Now you're all excited, right? We have the golden rule of organic chemistry. Strong acids have weak conjugate bases. Is that the golden rule? I don't know. Whatever. We're for now, at least for this week, that's the golden rule, right? So now the question is, what makes a weak conjugate base? How do we identify weak conjugate bases? So there's four things that we're going to look at. Two of them are really important that come up a lot, and two of them are kind of very specific ideas that aren't going to come up quite as often. So we'll start with the two big ones, and then we'll do the two kind of more niche ones and go from there. All right. So stable conjugate bases. The first thing that we're going to look at is we're going to look at trends in the periodic table. Now, this is easier to do in a classroom because there's usually a big periodic table to look at, but we're just going to assume that you guys kind of remember what the periodic table, what is where on the periodic table. So I'm going to draw in a couple of kind of the upper right corner of the periodic table. So here's carbon, nitrogen, oxygen, fluorine, chlorine, bromine, iodine. Right? And so we're just going to compare how acidic are things that are attached to these elements, right? So if we look at the simplest case of a hydrogen attached to carbon, we'll just use CH4. Right? The pKa of methane, CH4, is about 50. This is a very large number. Methane is a very terrible acid. Right? It is a very, very, very weak acid. So we have weak acids over here. Next up is ammonia, NH3. Ammonia has a pKa of about 38, so smaller than hydrogens attached to carbon, but still very much a weak acid, right? pKa of 38 is nothing that anybody's too excited about. Next, we get to H2O. H2O is, of course, water. H2O has a pKa of about 14. Not about 14, it has a pKa of exactly 14, right? Since that's one of those rules that you learn in Gen Chem. And H2O is neutral, right? So not a very strong acid at all. It will only act as an acid if it's in the presence of a base, right? But you can notice, of course, H2O is a much, much stronger acid than ammonia or methane. And so the trend continues. If we look at HF, then of course we see that the pKa of HF is 3.2. And so now we're getting towards stronger acids, right? HF is still not a particularly strong acid, but we'll say it's a stronger acid, right? So as we go across the periodic table, right, as we go from left to right across the periodic table, we go from weaker acids to stronger acids, right? And this is basically just an electronegativity argument, right? You have a more electronegative atom attached to the hydrogen, which means that you have more, which means it's more like H plus, right? If you look at the HF bond, the fluorine is very electronegative. The fluorine is going to hold most of the electrons on its side of the polarized bond, and so the hydrogen will have a pretty large delta plus on it. If you look at methane, there's no dipole there, no polarization, and so the hydrogen will have no delta plus character associated with it. And so, of course, it's not going to act as H plus because there's no reason for it to do so. Right, so electronegativity is the argument that we use to justify this trend, that as we go to the right of the periodic table, the pKa gets lower and the acid gets stronger. Now let's look at the halogens. Oops, I skipped right over chlorine. So the halogens, we have HF, HCl, HBr, and HI. Right? HF we've already established has a pKa of about 3.2. HCl is a pKa of -7, HBr is a pKa of -8, and HI is a pKa of -10. So of course, once again, we're going from weak acids. HF I would still classify as more or less a weak acid to very, very strong acids, right? HI is about as strong of an acid as we can get. And so as we go down a group in the periodic table, our acids become stronger. And this is true of every group, right? So if we were to start at nitrogen and move down the nitrogen group, so we get to phosphorus here and then arsenic, right? These hydrogens attached to nitrogen would be weaker acids than hydrogens attached to phosphorus. Those would be weaker acids than any hydrogens attached to arsenic, right? No matter which group you go down, the trend is always the same. The acids get stronger as you go down. This argument is based on size. Um, atoms get larger and so hold the hydrogen less securely. Right? And this is kind of a weird argument to think about, but basically the atom gets very big, the hydrogen gets further and further away from the nucleus, the electrons aren't held as tightly, right? So an iodine atom is this massive cloud of electrons, and so those electrons aren't really, the electrons out in the valence shell are not very tightly held by anything, and so when they bond to a hydrogen, that hydrogen is easy to kind of fragment off and create H plus, right? And so the size thing is a little bit kind of hard to wrap our minds around, but this is the argument that we make. But the trend is, as we go to the right and as we go down, acids get stronger. So HI is one of the strongest acids that you're going to find in the periodic table, right? So one of the ways that we determine if a conjugate base is more stable is we look at what is the hydrogen attached to? What element is the hydrogen attached to, right? And then we use the periodic trends to tell us, yeah, if the conjugate base is stable, right? So as we create a more electronegative element, right, the conjugate base of HF is, right, if we react this in an acid-base reaction, the conjugate base is F minus. F minus is a nice stable anion, right? That's not a terrible thing because fluorine is so electronegative, it can be very stable as F minus. Similarly, if we look at HI, the conjugate base of HI is I minus, and of course, I minus is a perfectly stable anion. Because iodine is so large, it can distribute that charge all over the place, and so we have a very stable conjugate base associated with our very strong acid of HI. Right? So once again, the stronger the acid is, the weaker, the more stable that conjugate base is, and that is borne out in the periodic trends. As we go to the right of the periodic table, as we go down a group in the periodic table, we come across stronger and stronger acids when we have hydrogens attached to those elements, right? So notice, of course, that the carbon-hydrogen bonds, right? So remember that when we were drawing our structures in the first unit, those carbon-hydrogen bonds, we didn't even draw them in because they're so unreactive. And this is it, right? They don't create a stable conjugate base. Putting a negative charge in carbon is not good news. We know that from resonance, right? Our resonance rules and stuff. And so there's no reason to remove those hydrogens because they don't create stable conjugate bases. And so they're not strong acids. And so they don't react. And so there's no reason to draw them in. Okay, so we're pulling that stuff through here, right? We got resonance, we got structure, and now we have reactivity as well. Okay, the second thing that makes a stable conjugate base is resonance. Resonance stabilized conjugate bases. So if you thought we were done with resonance, you are sorely mistaken. So let's compare these two hydrogens. We have a hydrogen here and a hydrogen here, right? And so which of these is going to be more acidic? More acidic? To figure that out, we think about what are the conjugate bases of these two hydrogens. So if we remove this hydrogen, right, we end up, and it doesn't matter what the base is in this case, because all we're considering is the conjugate base. Right? The conjugate base is this O minus. Versus this one, where again, we create O minus. So here our periodic trends don't really help us, right? Our periodic trends tell us putting negative charge on oxygen is generally okay. It's an electronegative molecule, right? So it's better than nitrogen, But in this case, if we're comparing these two, both of them have negative charge on oxygen. And so periodic trends don't distinguish between these, don't see a difference, right? Negative on oxygen in both cases. But what's different about these, of course, is that in the second case, we have a pi bond that's near our lone pairs, right? We're creating extra lone pairs when we remove that hydrogen because our base, whatever our base is, right, comes in, makes a bond to the hydrogen, we break the bond, and we create a lone pair, right? So we're doing the same thing over here too. Make the bond, break the bond, create that lone pair, right? So we have a lone pair here. We have a pi bond here. We have no pi bond in this molecule, right? All we have are neutral sp3 carbons. And so this molecule cannot be stabilized by resonance. Right? Because there are neutral sp3 carbons, and neutral sp3 carbons be cannot be a part of resonance, right? That was one of our rules that we learned in the first chapter when we talked about that stuff. So now that we recognize that, we can immediately point to that molecule and say, no resonance there, nothing but neutral sp3 carbons. On the other hand, where we have a pi bond, we can use these lone pairs to make a new pi bond and use these pi bonds electrons to make a new lone pair. And so we can draw a resonance form of this one where we have a pi bond there, and now we have a negative charge on this oxygen. And so what we've done, of course, is resonance distributes that charge, which if you remember back to a couple weeks ago, means that that charge is more stable. Right? And so what happens when we have a more stable conjugate base? I hope that you just shouted, we have a stronger acid. I can't hear you, but I hope that you shouted it because that's what I make my classes do when we're all in the same place. So pretend that I stood there a while in awkward silence until somebody said strong acid, because then you'll get the full experience. Okay, so to write this all out, if the conjugate base is stabilized by resonance, the acid is stronger, right? So the question, which of these two is more acidic? The answer is this one here. And the reasoning behind that is that the conjugate base has resonance stabilization. So because it has a resonance stabilized conjugate base, it is the more acidic molecule. Okay. Okay. This video has gone on long enough. We got through two examples of stable conjugate bases. The first one is through periodic trends. The second one is through resonance. So two. Right? We'll go through the other two in a real quick video here in the next ones. The next two are, like I said, less common. Most of the time you're going to see either periodic trends or resonance, but there are a couple of others. So we'll go through those really quick. The next video will not be 15 minutes long. And then and that'll do it for acid strength. See you in the next one.